In this lecture, I want to talk about differentiability at a point. We talked about the definition of the derivative at a point already in a previous lecture. So we said that f prime of a was the limit as h goes to 0 of f of a plus h minus f of a over a plus h minus a. What I didn't say in the previous lecture, which is probably important to mention, is that this simplifies. You could already figure that out, but I just want to mention it because this is the form that you will see in most textbooks. Alternatively, we said another way to define this is to say the limit as x approaches a of f of x minus f of a over x minus a. So the question is when, well, before I say that, we also said that this was the slope of the tangent line. Slope of the tangent line. Which tangent line? The tangent line to f at x equals a. All right, and then we also said it's instantaneous rate of change at x equals a. All right, so the question that I'm posing in this lecture is, when is a function not differentiable at a point? When do we not have the slope of the tangent line to a function? When is the instantaneous rate of change of a function undefined? These are all kind of equivalent ways of saying it. But if you go back to our definitions here, this one and this one, notice that in both cases, the definition is a limit. All right. Remember, this is the slope of the secant line. These are both expressions for the slope of the secant line. This secant line goes through a f of a and a plus h f of a plus h. This one goes through a f of a and x f of x. But that secant line, remember what this limit does is bring those points together so that we end up with the slope of the tangent line. So another way of asking this question is, when does that limit not exist? So first, I want to just kind of give a brief summary about when the function can fail to be differentiable at a point. So the first is when f is not continuous at x equals a. So I'm going to just give kind of very more intuitive explanations to begin with in this summary, and then go back and look at how this relates to kind of these expressions, these algebraic expressions. So let's think of a function that's discontinuous at a point. So let's say, for example, there's a hole here, right? So of course there's lots of ways to be discontinuous, but one is to have a hole at that point. All right. So let's say this is our function. Let's put it on the xy axis. Now, there's a lot of places along here where there are tangent lines, right? I have right at this point, I can have a tangent line. I can have a tangent line here. I can have a tangent line here, a tangent line here, but it doesn't make any sense to have a tangent line here. I can't have a tangent line to a curve where there is no curve. All right. Another way to think about it is you can't have a tangent line to a point, just a single point sitting out in space, right? Because this could be defined up here, right? But the tangent line has to be to the curve, which means there has to be some continuity at play. The function has to be continuous at the point. Because here, how do we know what's tangent, right? Which direction do we draw this thing? If it's just a point sitting out in space, likewise, we could have had something that was like this, where it was, so this is a removable discontinuity. What if I had a jump discontinuity like this, right? When I get to these endpoints, how do I know what direction because it's just a point, I could be kind of tangent in any direction, all right? Tangency kind of requires continuity, and this is kind of how to see it somewhat intuitively and graphically. A single point, we wouldn't know which direction, what the slope of the tangent line would be. So this is one thing. We have to have continuity. That has to be there in order for me to be able to actually draw the tangent line. And this type of thing won't work because we don't know what direction that the slope of the tangent line would be there. Okay, so that's one. When f is not continuous at that point, then I should finish the sentence. Then f prime of a, the derivative of f at a, does not exist. All right. What's a second one? We could have a vertical tangent line. All right. So you recall from algebra that if I have a vertical line, something of the form, x equals a, right? So I don't know, like let's look at like x equals 2. What does that look like? Well, here is my xy plane. Come out here to here. Here's the line x equals 2. Well, what's the slope of that line? Remember, with vertical lines, we said that the slope is undefined. All right. So if we were to have, for example, a function that did something like this, and it kind of went up like this, and then kind of came back, right? So there might be a point at which this thing goes completely vertical. Just for a moment. It can't be there for very long, right? Because otherwise we'd end up not having a function. We would have two y values associated with a single x value. But if it were just to kind of at one particular point, the slope of the tangent line, so we would have tangent lines here and here and here, and coming up to it we could have tangent lines like this, right? But at one particular point, maybe I should redraw that in another color. We come in right here and boom, it is completely vertical right at that one point. At that particular point, we can call this point x equals a, we would say that f prime of a does not exist, all right, because it's got a vertical tangent line. Okay, one more case is called a corner point or a cusp. All right. So a corner point would, it would look something like this or this. I mean, basically a corner point, you have basically linear functions, whereas a cusp, they might not be linear. It could be curved. So you could have something like this or something like this. And again, we think about what's going on here. I think it might be easiest to see in come on, green. Something like that's curved, we have tangent line, tangent line, tangent line, and it seems like it's going like that, right? But if you come in from the other side, you have a tangent line like this, a tangent line, tangent line. So as you come in it from both sides, the slopes of the tangent lines, again, so let's go ahead and put this on the xy, in the xy plane. Right at this point, if we call that x equals a, if you approach it, think about the limit, right? If you think about the slopes of the tangent lines coming from the left and from the right, they're not going to agree at that point. The slope of the tangent line won't exist because these slopes coming from the left and the right aren't going to agree. You have to question about, well, which one are you going to use? Are you going to use this one or are you going to use this one? All right. So similarly here, you would have, well, the slope of we haven't talked about this yet, but you take the slope of or tangent line to a line, does it make sense? It's just going to be the same line, right? I mean, when you take a tangent line to a line, and similarly here, so again, you have this thing where right at this particular point, right there, depending on which side you're coming at it from, the slopes of the tangent lines aren't going to agree. So if it, again, put this in the xy plane, call this point x equals a. In both of these cases, we say that f prime of a does not exist. So I just want to now give you a couple of examples that we can look at of each of these. So quick review: if f is not continuous, then f prime of a does not exist. If we have a vertical tangent line, then that point where the tangent line goes vertical, f prime of a doesn't exist. And if we have a corner point or a cusp. So let's think about something like, so for an example of 1, we could think about the function 1 over x at x equals 0. So quick sketch, we have this, right? So clearly the function is not continuous at 0. Why? Because it's not defined at 0, right? Remember, for continuity, we need that the limit, in this case, the limit as x goes to 0 of f of x to equal f of 0. That's continuity. So we need this limit to exist, and we need this function value to exist. But for this function, that function value doesn't exist. And if you think about it, again, if we're doing tangent lines, you know, along here, here, and here, 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 you know, there's going to be this jump, right? You can't have a tangent line to the curve where the curve doesn't exist, all right? So that's one example. It's worth noting that if the function is differentiable, then it's also continuous. So I just want to, this is a very brief proof that I just want to show you. So this is kind of an important idea. What it's saying is that if f is differentiable, then f is continuous. All right, another way to say it, so the reverse is not true, and we'll actually, I'll come back and show you an example of that. So it could be continuous and not differentiable, just like the limit might exist, but it's not continuous, right? So if you have something like a hole, like a function like this, the limit exists because these converge to a single point, but it's not continuous at that point. So we say that basically continuity is a stronger condition than the limit existing. It takes more for it to be continuous. Same thing with differentiable and continuous. Differentiable is a stronger condition than continuity. It could be continuous without being differentiable, but if it's differentiable, it's automatically continuous. All right, so I just want to give you a very brief, somewhat intuitive proof of this. And I'm going to use this this definition back here. I want to use this definition to show it. All right, so we're starting off with f is differentiable. So that's what we're starting with. And ultimately, we want to show, so I'm sorry, I should say differentiable at x equals a. And so what we want to show is that the limit as x approaches a of f of x equals f of a, right? Because that's our definition of continuity. All right, so if we look at this, I'm going to start just kind of with this right here, because that will help us to think about the derivative. We need to kind of get the derivative in there somehow. So I'm going to start with f of x minus f of a over x minus a. All right, and I want to set that equal to f of x minus f of a. Now, this is not always intuitive, but you'll see kind of where we're going. It's a little bit of a trick, but at least you can kind of see why we want to have this piece in here, because it's related to our definition of the derivative. All right, well, these aren't equal, right? But if I do this little trick here and I multiply over here by x minus a, notice that now they are equal, right? Because these would cancel, and I'd have f of x minus f of a equals f of x minus f of a, okay? Now, I know that for this to actually be the definition of the derivative, I have to have a limit in there. And then notice for continuity, I also need to have a limit. So what I'm going to do is I'm going to take the limit as x approaches a to both sides. So this is this whole thing over here, and then for this whole thing over here, times x minus a. Okay, now remember that the limit of a difference is the difference of the limits, as long as we know that those limits exist. So this up here, just fold it over to see where we're at. Okay, so this is where we were. So let's pick it up from there. Actually, I'll move it over this way. Okay. So I'm going to say now that I have the limit as x approaches a of f of x minus the limit as x approaches a of f of a. I also know that the limit of a product is the product of the limits as long as those limits exist. And I know this first limit exists because, again, going back this limit right here, that one exists because we assumed that f was differentiable, and that's what this means. So we know that that limit exists. So we have the limit as x approaches a of f of x minus f of a over x minus a. I know this one exists because that's just a linear function, right? It's just x, like x minus a is something like x minus 1 or x minus 5, x minus 10. So I can write this, the limit of this product is the product of the limits. Okay, now this I don't know anything about yet. But notice f of a is just a function, right? It's the function evaluated at some particular point a. So the limit of a constant is just the constant. So that's just going to give me f of a. This piece right here, that is the definition of f prime of a. And this piece right here, that's continuous, right? So I can just put in a. If I put in a, I get a minus a, which is 0. So this piece, all of these, this equals this, it all equals 0. So if this equals 0, then I could just add f of a to both sides, and I'm left with the limit as x approaches a of f of x equals f of a. That's what I wanted to show. So again, what did we show? We showed that if a function is differentiable, I should say at x equals a, then it is continuous at that point as well. Okay, that's an important idea. I didn't want, and it seems relevant to mention it at the point when we say that if a function is not continuous, then it's not differentiable. So differentiability kind of relies on continuity to some degree. It's not the only thing it relies on, but it certainly relies on that. Okay, let's look at our second, just a specific example of the second one, this vertical tangent line. I'm going to give you a graphical example, but let's look at a vertical tangent line for a specific function, and this is actually a pretty familiar function. Let's take a look at f of x equal to square root of x. So graphically, we have this thing, it looks like this. And so what we're saying is that as we get close, well, the issue here, if there's going to be an issue, notice it's going to be at x equals 0, because we can draw in tangent lines along here, and they're becoming steeper and, well, okay, got to touch it. Yeah. They're getting steeper and steeper, right? But right at 0, this thing goes completely vertical, all right? It may not look like it from the way that I drew it, just with kind of a rough sketch, but it does, right at 0, it goes completely vertical, and so we would say that at x equals 0, f prime of 0 does not exist. I guess it's actually a little redundant, but the function is not differentiable at 0. That's the most direct way to say it. Let's look at how that could be algebraically. So if we take the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Well, this is our function right here, so I'm going to have the limit as x goes to 0 of the square root of x minus the square root of 0 over x minus 0. Well, that's just going to give me the square root of x over x. But notice that x can be written as the square root of x times the square root of x, right? Square root of x times the square root of x gives me x. So now I can divide out one of these, right? Square root of x divided by square root of x is 1. That leaves me with 1 over the square root of x. Now if we take the limit of that as x goes to 0, what happens is our denominator gets smaller and smaller and smaller. Notice that technically we're actually taking it from the right, because square root is only defined for positive values, so we can only come at it from the right. So we're taking the limit as x approaches 0 from the right, so this is going to tend to infinity, because 1 is being divided by smaller and smaller and smaller numbers. All right, so this is kind of a way to show you algebraically how we can confirm our intuition graphically that the tangent line is vertical at that point. All right, last example. I want to talk about this last one where you have a corner point. All right, so our example for that one, is to let f of x equal the absolute value of x. All right, so if you recall the graph of absolute value, so remember, so the derivative is the slope of the tangent line, and the slope of the tangent line to this part right here, right? So any line drawn tangent, so just to kind of show that again, any line that could be drawn tangent to this would actually be right on top of the same line. So the slope of the tangent line is the slope of the line, and out here the slope is 1 because this part of it is y equals x. And over on this side, we can draw the slope of a tangent line. Again, it's right on top of the function, and the slope of the tangent line is the same as the slope of the line, and over here the slope is -1. All right, so we see that we're going to have an issue right here with the slopes of the tangent lines. There's no way to really determine what the slope of the tangent line is because as we come in from both sides, they seem to conflict. Let's see how we can use our definition. All right, so the first thing is to recall the piecewise definition. Well, I'll tell you what, let's start with just our definition and we'll come back to the piecewise definition. Limit as x approaches 0 of f of x minus f of 0 over x minus 0. So this is our function, so this is going to be absolute value of x minus absolute value of 0, which is 0 over x minus 0. That's going to leave us with absolute value of x over x. This is where the piecewise definition could be useful. So we could rewrite this as absolute value as x when x is greater than or equal to 0, or negative x when x is negative, right? That's what we have going on right here. This side of it is y equals x, this side of it is y equals negative x, all right? So now we're going to have to break up this limit into the left and right hand limits. So the limit as x approaches 0 from the right, well, from the right, we're on this part of the domain, right? Whoops, sorry. This is for x greater than 0 and for x. It equals x when x is greater than or equal to 0. It equals negative x when x is less than 0. Sorry about that. So if we're coming at it from the right, we're looking at this part of the domain right here. So absolute value of x is x. So I have this, but that's the limit as x approaches 0 from the right of 1, and the limit of a constant is just the constant. Coming at it from the left, so now we're on this part of the domain where x is negative, absolute value is negative x over x. Well, that's the limit as x approaches 0 from the left of -1, right? Because negative x divided by x for any value of x is -1, and that gives me -1. So notice that what happens here, this limit that we started with, which is f prime of 0, is we can rewrite it as the left and the right hand limits, but the left and the right hand limits don't agree. All right. If we were to actually graph this, we would see that we get something that looks like, if that's 1 and that's -1, we get a function that looks like this, right? So that limit doesn't exist. This limit that is the derivative does not exist at that point. Okay. Last thing I want to mention about this is I want to point out that this is an example of a function that is continuous at 0, right? Because, well, we've examined this, but the limit as x approaches 0 of the absolute value of x equals the absolute value of 0, right? That's the definition of continuity. So absolute value is continuous at 0, but it's not differentiable. F prime of 0 does not exist. All right. So while a function has to be continuous in order to be differentiable, that's what we were saying with our very first point here, is if f is not continuous, then it's not differentiable. This is an example of a function that it is continuous, but it's not differentiable. So we say the continuity is a necessary condition. It has to be continuous to be differentiable, but it's not what we call a sufficient condition. Being continuous is not enough to ensure that it is differentiable.